Hey kids, Mr. Murray here for Mr. Murray's Math Land, taking a look at another classic related rates problem. This one having to do with angle of elevation, so you can be sure that some trig is going to be involved. And in this particular problem, we have a rocket being launched vertically, given that its height can be modeled by this function, h of t equals negative 16t squared plus 40t, that classic position function of objects in free fall. Might look familiar to you physics fans. If you're in, feet per second, that is. If you are in the metric system, that would be a negative 4.9 t squared there, just for fun here, to draw some connections to what you did previous years. And in this case, we have this rocket being launched vertically, and an observer is standing 32 feet away. So there's my rocket being launched straight up, I believe, so that we can assume it's perpendicular, giving us a right triangle. We have an observer down here, 32 feet away. I don't know why you'd only be 32 feet away. Maybe it's a bottle rocket, like a firework. But again, a big thing with related rates is, of course, using variables for quantities that are changing and not using variables for quantities that are fixed or constant. And that can be tough to get that balance down. But what is changing in this problem? The rocket's going upward, so its height is changing. So I'm going to use a variable there. It may as well use h for height. And h is given by this equation here. The observer is 32 feet away. That is not changing, so that I'm going to label as 32. As the rocket is going up, certainly that observer's angle of elevation, that is going to change, so I'm going to use a variable there. I'll call it theta. And we are trying to find the rate of change of that angle of elevation 1 second after the rocket is launched. So I'm trying to find d theta dt, rate of change of the angle, but at a very specific moment when t is equal to 1. Okay, so let's take a look at what we've got going on here. Hopefully you can see, theta is changing, h is changing, 32 is fixed. How can I relate these three quantities? And by the way, the hypotenuse would be changing also if the question were to ask a variation of, say, how is the distance between the person and the rocket changing after 1 second? Then I'd be looking for the rate of change of this variable. But they don't mention that, so I'm going to set it up using these three quantities. And that would be tangent. You've got your angle, that's opposite. This is adjacent. So the easiest way I would say is, let's establish that no matter where the rocket is, the tangent of theta is always going to be equal to that opposite height over the adjacent 32. Now, hey, we got this. Let's take its derivative, right? Let's differentiate. And we're differentiating with respect to time. Okay, so derivative of tangent of theta is secant squared of theta d theta dt equals, and this is just 1 over 32 times h. No quotient rule necessary over here. It's just a constant coefficient of 1 over 32, but times dh dt. And okay, you may be thinking, hey, they didn't give me dh dt. They didn't tell me how the height was, the rate of change of it. So this is an interesting little problem. So we're certainly solving for d theta dt. It's up to you whether you want to divide both sides by secant squared right now. If you like, you could do that. And when I divide by secant squared, though, dividing by secant squared is really just multiplying by cosine squared. So maybe it'll make things look a little nicer if I set it up this way. Okay, in the end, it doesn't really matter how you isolate, but this is what we're looking at here. So d theta dt, the quantity I'm really looking for, is 1 over 32 times dh dt times cosine squared of theta. And the key to all of this is this moment that it's specified, when t is equal to 1, so 1 second after it's been launched. That's what I need to know. You know, all of these quantities here, dh dt, cosine squared of theta, they all refer to, now that we're in the derivative, we're referring to these instantaneous moments. We're referring to when t equals 1, what are these values? So this is where you've got to imagine this triangle, when t is equal to 1, certainly that 32 is not changing. But what would the height be at 1 second? And so after 1 second here, I've got some things to find. Now, you've got that the height function is negative 16t squared plus 40t. So its height at 1 second, I'm going to plug 1 in and get negative 16 plus 40, which is 24 feet. So at this moment, when t is equal to 1, the height is 24. Which means, now that I know two sides, I could find the hypotenuse, because to find the cosine of the angle, I need the adjacent over the hypotenuse. Now these numbers are kind of big, and if you didn't have a calculator, remember the first thing you would probably do is think, hey, can I reduce it? Is it maybe just a Pythagorean triple? And if you divide each of these by the greatest common factor of 8, you'll see that's a 3 and that's a 4, which means it is a 3, 4, 5 triple, except it's all being multiplied by 8. So really this hypotenuse would be 5 times 8, or 40, at that one moment of 1 second. So the cosine is, of course, adjacent over hypotenuse, 32 over 40, which reduces right back down to 4/5. So that's another little lesson there. If it is a triple, you can use the reduced members to find any trig ratio. So the cosine is 4/5. So now I know this part, 4/5 squared. The last part you got to find is this dh dt at 1 second. Well, again, you have a height function. So if you want the derivative at 1 second, take its derivative and plug 1 second in. So, you know, this is a little bit more involved than certain problems we've dealt with here. But here's the height function, or in other words, its position function, and h prime, which would be its velocity function, the rate of change of its height, dh dt, is the same thing as h prime, would be negative 32t, sorry, that was plus 40t, plus 40. So specifically, dh dt at 1 would be plugging 1 into this derivative, into this velocity function. And its velocity at that moment is 8 feet per second. You know, it's slowing down, it's getting near the top, but its velocity is still positive, it's still on the way up. So at this one moment of 1 second, dh dt, or h prime, is 8. The cosine of theta is 4/5. And now it's just a matter of multiplying it all out, simplifying. Notice I haven't used any calculator to do any of this. This is, you know, pretty basic stuff here. 1/32 times 8 is 1/4, times 4/5 squared is 16 over 25, where you could have canceled one of those 4's, leaving you with 4 over 25. And that's certainly the numerical quantity you're looking for, d theta dt, but if we want to write a nice little brief, concise sentence, we would say the angle is increasing because it's a positive rate of change. Always nice to use the word increasing or decreasing in your answers here to reflect your understanding of positive versus negative derivative values. The angle is increasing at a rate, also nice to include that, at a rate of 4/25, and the units are radians per second. Angles are always measured in radians in calculus, remember, because not just because they're nice, but that's because all those trig derivative rules are based on the fact that you are in radians in the first place. So always radians in calculus. Just remember that. And there we go. That's a little bit maybe more involved problem, but a good one to see. Hopefully it made some sense. If not, please ask questions. And as always, kids, keep it real. We'll see you later.